So this is topic 3.5, kinetic molecular theory. So the five basic key ideas of this kinetic molecular theory is that firstly, the gas has molecules in continuous and random motion. So all the gas particles are moving in continuous and random motion. And the second one is that volume of gas molecules are much smaller than the total volume of container. So even though there are a lot of gas molecules in a container, the size of the molecule, the particle itself, is much smaller than the gap between each particles. And third, the attractive and repulsive force between molecules are so weak that they do not significantly contribute to the motion of gas particles. And fourth one is that energy can be transferred through collision. So when they collide, when they hit each other, the energy is transferred through each other. And however, the average kinetic energy in the container or the substance does not change. And the average kinetic energy is proportional to temperature. So if temperature goes up, the speed of each particle goes up. And second one is kinetic energy and molecular velocity. So motion of molecule is the relationship between particles' kinetic energy and velocity. So this is the equation that represents the motion of molecule, where Ke represents kinetic energy and m represents mass of the particle in kilogram, and v represents instantaneous velocity in meter per second. And the key properties of this is that particles are in continuous and random motion, as I said before, and however they're not in same speed. So the kinetic energy distribution of the container or of the substance depends on the temperature. So temperature, if the temperature goes up, as I said before, average kinetic energy goes up. And the particle weight also matters. Where particle weight goes down, the speed itself goes up. And this is another equation for average molecular speed relationship. So this is the average molecular speed relationship, while R represents gas constant and T represents absolute temperature in Kelvin, and M represents the molar mass in kilogram per mole. And next one is another equation for temperature and average kinetic energy. So average kinetic energy is equal to 3/2 multiplied by the gas constant and temperature in Kelvin. And next one is the distribution table or distribution graph from Maxwell-Boltzmann. And this probability curve of speed of molecular speed shows the distribution of molecule speed in the container in given temperature. And the key features of this distribution is that the curve represents the fraction of molecules moving at certain speed. So this part, this much, this speed, this much. And most of the particles are near average. So this is mostly in this middle part. And the curve's area is the total number of particles. These. And the effect of temperature. So higher temperature means the curve is more flattened and more broadened. And most probable speed increases and average speed also increases. So here, high temperature energy or speed is more skewed to the right side than the lower temperature. And in lower temperature, the curve is in the opposite way, more narrower and more taller. So the speed cluster close to average, while the average itself is much weaker or much slower. And the number of high energy particles are obviously less than higher temperature. Lastly, the effect of molar mass on the speed is that the lighter or smaller molar mass leads to higher average speed, while heavier molecules lead to slower average speed. So as you can see in this graph, the O2, which has greater molar mass, has slower moving particles, while H2, which has lower molar mass, has faster moving particles on the right side. So this is just a simple summary table of the relationships and the concepts, and these are all what I have said today. Bye bye.